Log on, tune in, find out. Another good idea from Cambridge.
I don't have to introduce you anymore, do I?
Yeah. I wanted to mention this because I'm making these comments all the time about, I think I have it on, about the variance and standard deviations and all that sort of stuff. So what this actually is just instead of saying profiling the deviance, I could just say doing a whole bunch of likelihood ratio tests. That's really all that's involved in this. Let me just start off with an example. This goes back to 1947. Those of you who know about Davies' book, the book that was edited by Davies on statistical methods in research and production, one of those people who, it was an edited book, and one of the chapter authors was George Fox. And George happened to be working for ICL, is that right? ICI. I always get the two of them confused. ICI. And he was working in the dye stuff section. So these data actually came from George. And they had the a batch of an intermediate product. So they would get the intermediate product, and then they would make the dye from it, and they would look at the yields. All right? And in this case, of course, by the time the experiment was over, they'd used up all of that batch. So they weren't interested in comparing the particular batches. They just wanted to look at the variability that was introduced by this. So here, this is one of these nicely balanced, simple random effect models. In this case, we just have an overall mean yield, and then we have the variability within the batches. The batches here have been reordered so they have increasing means, and that blue line is just joining up the means. So you can see the variability between, and you can see the variability within. And if you go ahead and fit this, then you come up with, in this case for the Remmel fit, you have a certain value of the Remmel criterion, and you can get the standard deviations or the variance components, whichever way you want to think of them. I prefer to think in terms of standard deviations because then I can relate it back to the scale of the original responses. And then there's this, the estimate. Now, in this case, it's a completely balanced, additive, additive random effect. And so that's just the sample average. Right? There's nothing deep going on in here. And then you have standard error associated with it. I calculate the ratio of them, but then I don't calculate a p-value, and people always complain. Anyway, so if you're looking at computing power, you can talk about, well, I can work with very large data sets. But what if you're working with small data sets? Well, you can take the model and you can look at it much more intensely. So instead of just talking about standard errors, you'll notice here that there isn't a standard error, right? This is the standard deviation. So, am I doing right? This is simply that 42 is simply the square root of 1764. It isn't a standard error of the variance, right? And, if you get a variance and you get a standard error, then you naturally think of plus or minus, some multiple of the standard error. But then, why are we estimating variances? Well, I would claim because it's easier to write down the formulas in the analysis of variance. All right? You got these nice orthogonal relationships and so on. But why a standard error? Do we expect that things are going to be symmetric? In the simplest situation, as I mentioned, if you have an IID sample from a Gaussian distribution and you say, how do I get a confidence interval on the variance? Then it's going to come out of a chi-square, and it's going to be very asymmetric. So when you get outside of the perfectly balanced case, and I always tell my students that even if the experiment starts off going to be balanced, it probably won't end up being balanced. You know, one of the rats eats another rat or something. And, you know, Murphy's Law will come into play and you won't end up with a balance. Or in these large longitudinal studies where, you know, you're recruiting patients, or in my case, students all over the time, you never get equal numbers of observations. So if you want to go back and look at the F and T statistics, they don't really end up with those distributions. But if you want to talk about the likelihood ratio test, then you can fit the model with the particular term, and you can fit the model without the term, and you can look at the change in the deviance, and you can relate it to the number of parameters that are gone in there. Now, admittedly, this is, you know, the difference in the deviances is a reasonable way of assessing the quality of the fits. It's just a matter of, should you be comparing it to a chi-square? All right. So it's not a question that this is a dubious way of assessing the variability between the two fits. It's just a matter of what do you compare it to. And I particularly like it because in the case you're going to fit both the full model, the alternative hypothesis, and the restricted model. Some of you may know that I started off working in nonlinear regression, and you know, often had this situation where you say, okay, at this point, you're assuming that the change of the residual sum of squares, or the change of the likelihood with respect to the parameters, is going to stay nice and linear, but it doesn't. So then you have to adjust for that. So here, you know, if it's only going to take you a couple seconds, you might as well fit them both. So now if you wanted to go back and you wanted to consider a hypothesis test, and then the confidence interval, well, of course, the confidence interval is those values of the parameter that are not rejected by the hypothesis test. And so for the fixed effects models, it's possible to determine the change for a model that doesn't have any random effects. Then you can determine the change from the full model fit only. But as soon as you start working with these random effects, changing one of the parameters can start to change those variance components. You know, you just got more things in motion here. So you might as well fit both of them. Right? So in practice, what we do is we take a particular value of the parameter at the estimate, and then you change it a bit. And you refit all of the other parameters. And you look at the change in the deviance. And then you go out a bit further and you look at the change in the deviance. And then you go over in the other direction and you do the same thing. If everything was well approximated, you know, if the likelihood surface looked quadratic over the region of interest, then these profile sections would also be quadratic. All right? So if you had a perfectly quadratic likelihood surface, the reason it's called the profile is that you're sort of standing back and you're looking at it from one direction and you're seeing the profile of the surface. All right? Yeah, I'm doing the likelihood surface there. The deviance surface, of course, is upside down. And then, so here, if we were to get that series of likelihood ratio tests and look at the difference in the deviance, it should be quadratic. It's hard to assess whether something really looks quadratic, so you take the square root, right? Because you got the change in the deviance, you're at 0 at the estimate. Then if you flip the left-hand side, right, you're moving the parameter from the estimate positive and negative, you might as well flip over the left-hand side, and now you get something that should look like a straight line. All right? So that's called the signed square root transformation. Oops, pardon me. So this is the, it's too late. That's what I was trying to say, is the signed square root transformation. So you take the square root of the change in the deviance and you just apply a negative sign if you're on the left of the estimate and a positive sign if you're on the right. Okay, so here are those three parameters. There's the what's labeled here is intercept. It's actually just the mean response, all right? And then they have the standard deviation for, buttons are too close together, where my fingers are. So this is the standard deviation for the random effects, all right? Now, I have switched here from the Remel fit to the maximum likelihood fit. So in the case of the Remel fit, this estimate was slightly above 40, and now it's just slightly below 40. It turns out, and I look at the logarithm of the standard deviation of the noise, which of course is just a scaled version of the logarithm of the variance. And the reason for doing that is this one can never go to 0. It can't go to 0 unless all of your data have the same value, which you'd probably notice before you fit the model. Whereas this one can, and in fact it does. As you decrease that value, it loses sensitivity. The model loses sensitivity to that particular parameter, because down in this region, all of the random effects are being forced to 0. And so it ends up giving you the same deviance. The deviance just flattens out at this point. Here, this is the effect that it's over-dispersed relative to the Gaussian, right? And that's sort of what you would expect. In fact, because this is perfectly balanced, you can use t-distribution on this. And so that's just indicating that it's a little flatter than what you would expect from a Gaussian distribution. If it was exactly a Gaussian, that would be a straight line. Now, what happens when you take standard errors is, if you're looking at the information matrix, you're looking at the slope at where that crosses 0. All right? So that's where you're getting your standard error from. And then those vertical lines are, if I take, notice that one of them is just a little bit under 2 and just a little bit over -2, so that's the plus or minus 1.96. So it's looking at the change in this square root, the change in the square root of the change of the deviance, and it's getting related to a standard normal. So this allows you to then go back and say, how far do I have to move that before suddenly my likelihood ratio test would start to eliminate this particular value of that parameter. So these are 50%, 80%, 90%, 95%, and 99% confidence intervals, except in this case, the 99% goes all the way to 0. All right? And this is just another representation of it. It's back without taking the sign. This is just the square root, but it has the advantage that you can look at the intervals a little bit more cleanly on that one. You can also ask for the confidence intervals, which is just a way of getting these points where it cuts at the critical values on there. So these curves are actually generated by taking a few points. There's probably 8 to 10 points in each one of those figures, but the curves end up being nice and smooth. So when you're finished, you can do a nice job of interpolating on them. And this was changing the confidence level. So this is all a lot of text that just says, you can look at that and think of it as being like a normal probability plot instead of, but you're not working with a sample, you're working with the change in the deviance. But you can still see over dispersion, you can see skewness and so on in those plots. Here's what would happen if you did it in different scales. So you have the logarithm of sigma, which is just a scaled version of the logarithm of sigma squared. And then this is going on to the sigma scale, and it's starting to get skewed. And this is going on to sigma squared, and it's getting much more skewed. And the issue of whether or not you should be using Remel or maximum likelihood just means a small change in here, but it's not that much of a change relative to the uncertainty. Here's what happens if you go to that variance component of the random effects, all right? If you're going to work on the scale of the variance, then you're saying that this curve should be like a straight line over the region of interest. But it's nowhere close to being straight. You know, it's highly skewed on there. And if you are in the scale of sigma, well, you still have a certain amount of estimate minus a little bit plus a lot in here. It's actually nice and straight over this region if you go into the logarithm, but then you have this phenomenon that it can go to 0, and so it just flattens out, and it would flatten out and go indefinitely because the logarithm of 0 is going to go off to minus infinity. So that's looking at these variance components on different scales. Right? There's a few questioning looks. Have I lost anyone at this point? Okay. And also, by the way, look at the scale over here. That's a long distance to go out. Right? And then I realized afterwards that you could convert these to densities. And essentially, you've got a transformation that takes you onto the z-scale. So then you can just differentiate. You could change that into a cumulative distribution function, and then you could differentiate that and get a density. So this is not the density of the estimator, it's more about the sensitivity of the estimation criterion, the deviance in this case, with respect to a particular parameter. But if you had something that started off with a density like that, you'd get exactly this behavior. So this is not exactly talking about the distribution of an estimator, but it gives you a pretty good idea of what's going on with the distribution of the estimator. So down here, this is on the scale of the standard deviation, and if you convert, now this one, the labels are no longer correct, but if you converted and you went back, so this is labeled as if it was sigma 1, it's actually sigma 1 squared. This is labeled as if it was log sigma, it's actually sigma squared. So this is what I was saying, that there's a tremendous amount of skewness to this. And your two estimates, whether they're maximum likelihood or REML, are both over in this area. And so it's a question of, is this a representative? And that's what I was getting at the point about unbiasedness. Unbiasedness, you're relating the expected value of the estimator back. So you're thinking about, well, what point could I balance this curve? But it's so highly skewed that the mean is not a good representation of that. So then you can use a bit more information. And those of you who've seen what Don Watson and I did about nonlinear models and profiling, this will sound familiar. When you're doing this conditional optimization, so you take one of the parameters and you move it to a new value and you optimize all the others, you not only get the best value of the deviance that you can get for that value of the parameter, you find out what the conditional estimates of the other parameters are. Okay, so we refer to those as the profile traces. As you move one parameter, how does it drag the other around? Okay. And the other thing to realize is this is a transformation. It's an empirical transformation, but it's a transformation so that I can take any value of the parameter within this range and I can say, okay, that corresponds to a certain zeta. And it has the property that when I take the parameters and I put them into this transformed scale, any contour will be enclosed in a square. And it will touch the square at exactly 4 places, because you've taken out all of the stretching and compression in one dimension. So anyway, let me go to the picture. It's easier to explain the picture. Well, it may not be. Now, I have to tell you, I have a programming error in here. And that's all of these panels all of these panels up here should be transposed. All right, so just remember that when I start to explain, it's not easy to keep track of what's the axes in there. So I got it wrong, and those panels should be flipped. Anyway, on the top, these three panels are in the original scale. Right? So this is the standard deviation of the random effects, 0 up to about 150. This is that log of the standard deviation of the residuals, and then this is that overall mean term. If I take any value, and these two lines across here are, as I change one of the parameters, how is the other parameter pulled along, right? So those are the profile traces in the original scale. Now, these two have the sort of optimal behavior. That's the fixed effect and the standard deviation of the noise term, or variance of the noise term, whatever. And they're orthogonal to each other. And in this particular case, because of the balance, they don't affect each other. It doesn't matter what you do to the variance components. The conditional estimate of the overall mean is still the sample average. Right? Whereas, and now I'm going to have to ask you to mentally transpose this figure. All right. So the other, what's showing here is a vertical line, should be horizontal. So it's again saying, if I change that variance component, I don't change the estimate of the mean. All right. It's all still the sample average. The other one is, if I start to change the mean and I take it away from the estimate of the average, then I'm going to introduce more overall variability. Right? I'm going to get larger residuals, and it has to go into either one of the variance components or the other. Now the balance means that it can't go into the residual variance, and so it goes into this one. So this, and again I apologize for the fact that this is transposed, but this line is, as I move the mean around, then that variance component has to increase to accommodate the additional variability. And then these two are looking at the two variance components relative to each other. And the thing that you should realize is that down in this area they kind of squeeze together a little bit. And so it's saying, if I decrease one of the variances, then the other one has to accommodate for it in some way. Right? Now, over here, this is after that transformation. Right? So I started off with these curves that gave me a transformation, and I take each one of the values on those particular traces, and I transform them, and then they produce a value over here. And then I got these little ticks. Now in this case, I have the perfect situation, right? Because I've taken out the one-dimensional nonlinearity, and I have completely orthogonal parameters, and they don't affect each other in any way. So those are all circles. Right? Down here, the parameters do affect each other in different ways. All right? Now what I said about the square is, it's obvious here that, and remember I have the same scale in each direction on those panels. So here, if you said, well, I can take a contour and I'm going to go out a certain distance on this axis, then I go out exactly the same distance on all the axes. Down here, it's also true. And from the positions where it crosses, if everything was perfect, you would stay with this figure. And down here, it is locally orthogonal, but it doesn't stay globally orthogonal. So then you have to distort it, and there's this method of doing it in terms of a phase and an angle and that sort of stuff. But anyway, it works very well. So based upon where these things are cutting, you can interpolate a contour, and then you can map it back. And so that's what gives you this one subject to the fact that it should be transposed, right? So you can take a look not only at the one-dimensional behavior, you can look at the two-dimensional behavior. Right? And if you change the scale, this is looking at the two variance components. Again, not software isn't quite as polished as it should be. And so those labels are wrong. But it's the variance of the random effect and the variance of the noise term. And that also has the transposition problem. But this figure is exactly the same as the one that was on the other scale. It's just the one-dimensional distortions that's changing here. But anyway, if you're going to say, well, you know, I'm going to base things upon the Fisher information matrix, and so, you know, de-optimality is related to the volume of certain ellipses and so on, this is what can be happening to you. You don't really have ellipses. You got some really distorted figures. So perhaps you want to go back to another scale and look at things in another scale on that, right? Anyway, those are the pictures, and thank you for your attention.
Thank you very much for these explanations. Any comments or questions?
Really easy one. Will the corrected picture and all the slides be available to us on the INI website or something?
Yes, I can certainly make those available.
I have another question, because when you do deviance like that, you still assuming that you could, for the confidence interval, you're using the chi-square statistics, so you're assuming asymptotics. So what happens when you have small sample size? Can you correct for anything? And because I understand you're taking into account the, you know, the linearity between these guys and so on, but you're still assuming that the change of 3.85 will be 95% confidence.
I haven't actually tried this, and I should. Essentially, the difference from using the standard normal to going to the t was to take into account uncertainty in the standard deviation or the variance. And this is essentially what's going on in here. Right. So one of the things that I could do is go back to go back to this one and say, well, in this case, you can come up with a t distribution because everything's nice and balanced. So how does that look relative to the t distribution and so on? So the fact that this is not a straight line means that it's looking at the uncertainty in those variances. And when you get this standard errors and correlations or variance covariance matrix for the fixed effects, that's actually conditioning. It's conditioning on a ratio of the variance of the random effects to the variance of the noise term. Right? And even if you have more variance components or other structures on the random effects, you're still conditioning in there. And then you're sort of trying to get rid of that by using T's and F's and adjusting and so on. So I think that in a sense, the adjustment's built into this, just because the fact that that's over-dispersed relative to the normal. But I haven't established.
And I haven't. Okay, go ahead.
Does this help you? I mean, one of the problems with small sample sizes is that you get the coverage wrong
Yes.
if you use small samples. You use classic information matrices without a bias correction.
Yeah.
That in some way, does this? Are you saying sort of that with small sample sizes, you're kind of halfway to the bias correction by inducing these strange transformations? Is that roughly what you're doing?
Not necessarily the strange transformation. The fact that you're refitting, the fact that you're refitting the model, conditional on a particular value of the parameter, but allowing all the other parameters to vary. So, as I was saying about the standard normal versus the t, one of the ways that you can think of that difference is that when you use the standard normal, you're saying, I assume that I have perfect knowledge of sigma, so I don't have to re-estimate it. Whereas when you use the t-distribution, you're taking into account your uncertainty in t. Now, this is getting into a more complex situation here because you have the different variance components. And so every time that you move that intercept, you're re-estimating the others.
It will improve your coverage.
I believe so. Yeah. That's the short answer. Yes, I could have just answered that, but I'm an academic, so I can't.
Last question.
Another question, do you have any idea why log sigma works much better, and how did you
Oh,
end
yeah.
up with log sigma? Is that mathematical?
Because I read Box and Chow.
Okay.
Yeah, I mean, in terms
Why
of
don't we have
the,
standard errors on log sigma much more often than on sigma squared?
I don't know. I think it's because the original equations were easier to write in terms of sigma squared. But, you know, Box and Chow talk about looking at things from a Bayesian perspective, and they talk about data translated likelihood. And so they would say that when you're working with a scale parameter, you really want to work on the logarithm. It's like, you know, when you're working with a rate constant, you want to work on the scale of the logarithm of the rate constant, and so on. So it's exactly the same flavor coming into here. Because, you know, taking a scale parameter and cutting it in half, on the other side, it's not going to 1.5, it's going to 2. You know, a lot of hand waving going on here, but I think you know what I'm talking about.
I suggest, I'm afraid that we need to finish because we have the poster session, but I'm sure there will be several questions to you on this problem or any other problem, and we will have a chance for discussion. The last point in the meeting on Friday afternoon is just discussion. So
Yeah,
I invite everybody.
If I can make one more sentence.
Yes.
Franz was asking earlier, why are you not getting the software out? It's because I'm getting the software to do that, including on the nonlinear models, not the generalized linear models.
So thank you for this explanation.